Very well, so far we have covered this conventional power supply. We will continue to advance with slightly more complex topics. Up to this point, we have been talking about conventional power supplies. However, in inverter technology, we generally find more complex power supplies, switched-mode power supplies. What do we mean by that? We refer to systems that transform electricity, modify it, and leave it ready to work. But they are more complex and more efficient. Basically, this change was made for the following reason. We are going to open a new board and start talking about switched-mode power supplies. The main reason is that here we have less hysteresis losses. We will not complicate ourselves too much explaining this because it is not relevant, but to explain it in a simple way, you remember that these transformers were always heating up. Always heating up. If you touched them, they were always hot. This is due to hysteresis loss, a resistance that iron exerts on the circulation of electrons, to say it in a simple way. Today, these switched-mode power supplies do not have hysteresis losses because the material with which the transformer is made is no longer iron, but ferrite. And that helps us in this aspect of not having hysteresis losses. In addition, another reason why manufacturers started creating these switched-mode power supplies is that they also save on materials, because now the transformers are much smaller. Those large and heavy transformers are no longer available today, and what we have is this. In a complex power supply, notice that we have the transformer the size of how many? Not even an inch. They are more complex. For us they may complicate us a little more, but they can be understood very well in any case. Now, let's gradually understand how they work. Today, we do not have the same circuit that we had analyzed. We do not have the same thing in a switched-mode power supply. We have the components, but in a different order, and that is what we want now. In a switched-mode power supply, we will have a voltage input, a fuse, a varistor, a double pi filter. You already know how all this works. After that, we go directly to that component that you already know how it works: a rectifier and a filter. The big difference is here. In a conventional power supply, we go to a transformer, we reduce the voltage, and then we go to the rectifier. That's why we enter with 12 and we come out with 17 in direct current. In a switched mode power supply, we go directly to the rectifier with 220 volts in alternating current, or 110 or 127. And we come out with a rectified of 310, 155, or 180. Be careful with these switched mode power supplies, because since you are already seeing that we are working with very high voltage, we have to be more careful when working with these power supplies. That is why these capacitors, the diodes, are not. They are usually the same 1N4007, but these capacitors are yes of more voltage, because they store much more electron power. Pay attention to this detail. In the next module, I'll explain capacitors and their characteristics, but right now, I'll continue explaining switched mode power supplies. So, what are we going to find now? We'll find a small gate. There's a detail that I don't know if you've already noticed or observed. I told you that any transformer has to work with alternating current, so the question is, if we had an alternating current of 50 or 60 Hz here, and we still have to go to a transformer, why would we rectify it and end up with 0 Hz? If we need alternating current for this transformer to be able to reduce the voltage. Indeed, as these ferrite transformers are so efficient and do not store heat, or do not prevent electrons from flowing from one side to the other, we can do the following. Instead of giving it 50 or 60 Hz, we take it to 0. And with this switch or gate, we take it back up again, but now with much higher frequency to be able to have much more output power in a much smaller place. So, at this point, thanks to this switch or gate, you'll find a frequency of 90 to 140 kHz. What do I mean by kilohertz? 90 kHz are 90,000 Hz. Imagine that the electrons are excited from one side to the other at that speed per second, very quickly. In a much smaller space, the same power can be supplied from the other side. That's the goal of switched mode power supplies. But how does this happen? How does all this effect happen? Let's look at it this way to understand it. We have a flow of electrons here, which pushes towards here and an output towards there, because this is direct current. With this component that is a gate that opens and closes commanded by another circuit, which we will discuss later, this component that opens and closes, what it will do is send electrons and let them stop passing. It sends electrons, they stop passing, it sends electrons, they stop passing. But what happens? When I send electrons from this side and make them stop passing, the electrons charged in the coil, they will circulate towards this side, crossing this bridge that you have here. This bridge is a diode. It allows them to pass to this side, but not to this. So I let them pass and they circulate towards this side. I cut the flow of electrons. The electrons that are charged in the coil, or that the coil is generating at that moment, as we discussed today, and that every coil generates electricity or pushes electrons, these electrons that are here push them to the opposite side and they are discharged through the diode. Thanks to that, you constantly have inputs, outputs, inputs, outputs of electrons, and a kind of alternating current is produced, but with a very high frequency, a frequency of 90,000 to 140,000 times per second. And that same thing comes out from the other side, but now yes, with a reduced voltage. On the other side, we don't have 310 anymore, but on the other side of this transformer we'll have 5 volts, always with a current, always with an alternating current, but with a very high frequency, which is no longer a sinusoidal and rather square this alternating current. It no longer has that sinusoidal format, but it doesn't matter, it's the same. As these transformers are so efficient, they allow manufacturers to put more outputs. They can have an output of 5, they can have another of 12, they can have another of 15, because they are very efficient, they work very well, and with so much speed, you can create what you want from the other side. All this allows these transformers. A component that they avoid putting is the 7805, because they can have several output voltages directly. The 5 volts are created directly after the transformer. This is very interesting. This detail is very interesting to understand and understand how they save money in other ways. Now, the question is the following. We want to see this component. We want to see it. We want to see the transformer on a board, and we'll see it now. In this video, we will see how switched mode power supplies work on boards. We will use the example of a board from an inverter kit from Goodweather or Panavox, as they use the same board. Let's take a look and get used to tracing the tracks on the board. We're going to pay more attention and zoom in a bit. With a lot of patience, we're going to trace the electricity or the electron circuits inside the board. We can see that there are 2 power lines, the line and the neutral. On one side, we have a coil, and on the other side, we have another coil. At this point, we have a capacitor, and at this point, we have another capacitor. These are the filter capacitors, and the coils also perform the same filtering function. If we continue along the path, we will go to this point. Now let's skip the fuse. We can see that the fuse and the varistor are a little far from the low-pass filter, but they are still the same components. Here we have the line. We skip the fuse. This is the fuse symbol. We see it here. And here we have the varistor. As you can see, it is stored in this plastic. Here it tells us its voltage. If we continue to travel, we can see that here we only have bridges to be able to jump this track. These would be the W28 and W29 bridges. Following the path, we find a small thermal resistor that protects against any high temperature in the area, but simply the electrons pass. At this point, we find the 4 diodes. These 4 that are here that I have marked in black are the 4 diodes that produce rectification. From here, we jump with this to here, and with this to here, and with this to this point, and with this other to this last end. We will see how the diodes are configured from neutral and from the line. Let's see who 2 diodes we find from each side. Notice that we find a diode in reverse, another in direct, the other in reverse, and the other in direct. These are the ones that will produce the rectification. Then, from the side of the positive, which is this point that we have here, we will find the 5th diode. As I told you, it makes a division between the effect of the capacitor and the unbuffered rectification. From this intermediate point, before the 5th diode, is where a sample will be taken to this circuit, which I will explain later, which is the zero crossing detection. From here the sample is taken. If we jump to the last diode, the 5th, here we have in parallel a capacitor to which some last noise filtering coils have been placed. It is very appropriate to place them in this area. Here we have another capacitor. In reality, what this manufacturer has done is to place 2 10 microfarad capacitors instead of one of 20 or 22, but has placed 2 of 10. Now, what do we find after? One of the 2 ends, or the positive, will go directly to the transformer. This is a repaired board, so you are seeing all these details. It will go to the transformer, the negative will pass through this component, and then it will go to the transformer. This component is the key that will be pulsing 90,000 to 140,000 times per second. The number of times it pulses will be fixed and constant, depending on the model of this component. These components have an 8-pin format, of which generally 7 are used. For example, here we can see a different model. These components have their input and output on opposite sides, and the rest are different signals that it will receive. Not to know how many times it will pulse, because that will be given to it by the same component. It is a fixed pulse. This transistor and this integrated circuit have a fixed pulse, but if there is something that will vary in the way it pulses, we will talk about it in a moment. How do we check the operation of this component that often burns out? This component, this switch, is a MOSFET transistor. If we compare it with water, it is a gate valve that allows water to flow and blocks it. It is simply that, receiving a signal to be able to open and close. The voltage it has to receive is approximately 15 volts. Then it opens, lets the electrons pass, cuts the passage, the electrons return, and through the return diodes is where the turn to the other side is produced, and the alternating current of the primary side of the transformer is created. Advantages and disadvantages of this source when repairing: it has many components and is not like a conventional power supply. This makes it more complex to repair, but it also gives it some advantages. The transformer almost never breaks. The other components, such as the switch and the diodes, are easy to find. This is another advantage because it makes repair more economical. So, how do you test the operation of this component that I mentioned a moment ago? We'll see. To test this MOSFET transistor, we will be analyzing it in the following way. We can observe in the circuit where the negative input is, and we can see the output to the transformer, which are usually the thickest tracks. When we have identified it, we need to put our multimeter in resistance mode and test between this input and this output. The resistance must be high. As we can see here, it must show us megaohms, very high kiloohms, or megaohms also, as in this case. Look, it looks a bit bad because of the light. Now yes, megaohms must be showing us. It has to go up and down, it has to be varying. In this case we have it in good condition, not only because of the component itself, but also because of all the components that are surrounded. This is the approximate value of a power supply in good condition. If it shows us OL in this case, something would be defective. Or if it shows us 00, direct continuity, surely something is wrong and the power supply will not work. This is because a transformer, if this switch is stuck, will receive direct current and will not work directly. This is an approximate value that a MOSFET transistor must indicate to us. If we had a switch outside the board and wanted to test its operation, we would have to do the following. We will grab the component, and we need to know its characteristics. Look, in this case, let's see if we can see it. Here we have one LN364PN. Here we can see one, but we are going to see a different model. This one I like more, it looks much better. TNY264PN, that's the number that's going to matter to us. Gradually, you will get used to it and you will know which code identifies them. The one at the top is simply a factory code, the one at the bottom is also a serial code, but the patent that indicates how this component is made up inside is TNY264PN. That is what you will be looking for on the internet. An electronics technician has to have access to the internet all the time today because many things that we are going to be analyzing we have to look for information on the internet. We will put TNY264PN in the Google search. This way we will have data about our component. We can go directly to images and we will have a drawing of how it is formed. Well, in the connections that have the letter S, this is source, there is where the negative will enter, where the electrons will enter. And at the gate D, that is the drain or output to the transformer. We grab our component. Look that we have a mark or guide that is always in electronic components of this format. Next to that point is the number 1. That is the bypass, and we will talk about it in a moment. The 2 and 3 are the same, they are the source. The 4 is the enable. 8 and 7 are different data. 1, 2, 3, 4, the 5 is the drain, 6 is not there, 7 and 8. Look that the 6 is not there. Well, what we have to test are 2 and 3 together with 5. So, let's do that test now to see how our component is. There we can see the number. Here we have 2 and 3, and there we have 5. Look, that 2 and 3 are in direct continuity. We had just seen that 2 and 3 were exactly the same. And between 2 and 3 and 5, 10 megohms, 11 megohms. This component is in good condition. 13 megohms, we are very well. As we could see, this is the way to test this component that is damaged quite a bit. If it is damaged, the best thing to do is to test all the components that surround it in the power supply, test them, and if everything is correct, replace it. If you cannot find the exact replacement, an adaptation can be made as we did on this board, but it is quite complex. You have to look at many more parameters, you have to cut tracks and make connections. That may be left for later, when you are more trained in electronics. But many times, or most of the time, we can replace it directly. In the case of this board, the original component was a Q100, a component I had never seen before. When it was damaged, we could not find a replacement anywhere. So we adapted a Viper 22A, which is universal and can be adapted with a little work. So we were able to make it work. But sometime later, in one of the classes, we discussed what had happened to me, and a student sent us the link where it was already on sale on AliExpress. Today, even the same one that we had not found can be obtained for replacement. These are details to consider with regard to switch mode power supplies. Of course, once this switch fails, you need to test the components around it. You need to take the time to test the diodes, which will be part of that return of electrons to create the alternating current. We need to test the resistors, which we still need to analyze so that you understand how they are measured. We need to test these optocouplers that we still need to analyze, and the capacitors that are surrounding the switch. These capacitors surround the switch and are part of the enable to activate or excite the transformer coil. Once we have tested them, we can come up with a solution to the problem if it is failing. In the next video, we will see the circuit of a switch. Next, we will see a brief circuit, so that you can see it in terms of electronic circuits and know how one of these switching power supplies is formed. I will show you as an example a TNY264. Here we have a TNY264. As you can see, we have several components that form this area of the power supply. We have a negative and a positive. This comes from the capacitors. From here we activate the source drain switch, we flow down to the transformer, and on the other side the current with reduced voltage is created. It is rectified again because remember that here we have alternating current. We will now talk about how the direct current is created again, and also about this very important detail in switching power supplies, about the possibility they have to regulate the power that enters the transformer to be able to deliver only the power that is used in the output. Let's see it. Let's go back to our diagram. Now comes a question. If we had alternating current, we transformed it to direct current to create an alternating current of much higher frequency. Now we pass through this ferrite transformer with alternating current, but with less voltage. Now how do we transform this back to rectified current again? Because to make the board work we need direct current. Well, this is done through a single diode. You remember that in a conventional power supply, or here in this rectification, we had the sinusoidal voltage. We rectified by bringing this wave up, and there we had a full wave rectification. After that, after the transformer, we will not do a full wave rectification, but we will do a half wave rectification. So what does that mean? What we will do at this point is the following. A single diode is placed, which is the one you will be finding. I want to show it to you on the board. You will be finding it at this point. One moment, I will show it to you. And with this single diode, we make a rectification. How is this produced? Imagine that these two will represent alternating current, and these two will also represent alternating current, but of different voltage. These two will be creating 12 volts, and these two will be creating 5 volts. So, what happens? Let's see. The electrons will enter here and enter here, and enter here and enter here, because this is alternating current with two different voltages. When the electrons enter here, this diode allows them to exit, but when the electrons want to enter here, this diode prevents them from passing. So, the electrons pass, stop, pass, stop. And the same thing happens with this one that produces the 12 volts. The electrons enter, pass, stop, pass, stop. As a result, in these circuits that are the circuits that will be powered with 12 volts and with 5, the electrons will always circulate in one direction. As a result, instead of having an alternating voltage that recovers the entire wave, we do not recover the entire wave in this case. In this case, what we do is, we lose half of the wave directly due to the blocking that this diode produces. As a result, we are losing half a wave and we only have half recovered. The other is lost, but it doesn't matter. Why doesn't it matter to us? Because only by placing a capacitor at these points, only by placing a capacitor here, and another capacitor, between this and this, with only these two capacitors between this point and between this and this, we can already keep the filtered current. We are not afraid that the voltage will drop so much since they are far from one crest to the other because the capacitor is charged. Remember that this happens 140,000 times per second. That is, a load from the capacitor to the next load is so fast that the capacitor does not discharge. So it doesn't matter that we don't recover this middle wave. We don't need it because this is so fast that we won't need it. This is a half-wave rectification, and this is the last filtering with capacitors, and there it ends. Having here already 5 volts, and here we have 12 volts. An important detail about these diodes, they are not normal diodes. Remember that they are like passkeys. They have to allow electrons to pass, cut, allow, and cut. Remember that this is very fast, 90,000, 140,000 times per second. That's why, instead of normal diodes, what you'll find at this point are Schottky diodes, superfast diodes. One moment, this part is complicated. They are not normal diodes. Their symbol is a little different from that of normal diodes. There they are, these are the diodes that are placed in that place. They are measured in the same way as diodes. We have to test with the multimeter from one side to the other, just like the previous diodes, but bearing in mind that they are different. They are superfast diodes. I'm going to show you all this on a board to see if we can follow up. Look, here we have been observing this board so far, and we were able to see We power the transformer, we go to the other side, and from this other side we now have a negative, which is usually the largest track, which is the one that is represented with G and D. And look that here we have one and the other positive. Here is a diode and here is another diode. This diode is in the 12-volt zone and this diode, evidently, in the 5-volt zone. Look, here we have a jumper, and it tells us that this is the 5-volt zone. In general, these boards have checkpoint. If we measure voltage between G and D and 5 volts, here we would have to have direct current, and between G and D and 12 we would have 12-volt direct current to know that the power supply works well. And we can also see the diodes on the other side. Here we observe two superfast and the capacitors, the last filter capacitors. Very well, here then we have the end of the switched power supply. I'll clean up the whiteboard a bit. This switched mode power supply is a bit more complex, so there are some things we still need to analyze. Let's clean up our whiteboard and leave it free so we can understand some parameters. Excellent. What is the circuit that opens and closes this gate? This circuit is composed of some more components. Sometimes, one of those components is an extra winding inside the same transformer that delivers 15 volts to power this switch. Sometimes it directly takes the 310 volts through a resistor. You will find all of those components surrounding the transformer and the switch. But what regulates this? Because there is something that is regulated here, it is not only opening and closing. What is regulated here is what we know as PWM. Pulse width modulation. What does this mean? You will remember that we had a constant alternating current here, which is given by the voltage of 50 to 60 Hz. But in this case we pass to 0, and then we pass to an alternating voltage, but already created by the switch. This speed is already given by the switch. It is fixed, but what we will vary is the pulse width. What does this mean? To understand it, let's draw PWM now. Now we will draw pulses in this area. The idea is that each of these points is almost at the same distance. This means that each pulse is at the same distance and speed. But what I can do is vary the width. Let's see if I can draw it and it turns out well. We would get up to there. Each of these pulses starts exactly at the same distance of time from one another, but what I am varying is the width of the electrons entering on one side and the width of the electrons entering on the other. This can be done by a switched mode power supply, and what regulates is the width of the wave that goes up. The switched mode power supply knows that on the other side of a half-wave rectification and the wave below is lost, so if more power is needed, it makes the top wave wider, and if less power is needed, it makes the top wave narrower. So, through a notice that the switched mode power supply has at this point, through an element that is warning or communicating from this side to this, it is informing the switch if more or less electricity is being consumed. Then it tells him how wide he has to pulse, the speed of it. But what is going to vary is the pulse width, the width of the wave that goes up, that is the one that is used. If it is being used less at that moment, it delivers less. If it is used more, it delivers more, but it delivers what is used so that through the transformer, it does not get excited and the voltage is lost afterwards. This is something that a conventional power supply cannot do. There is no communication. We cannot vary the pulse width because the transformer works directly with 220 volts, 50 Hz, or 60. And this is the advantage of a switched mode power supply. Of course, this implies that there are many more components that can break. The PWM circuit is a bit of a complex circuit, but this is what we find ourselves with. We have to learn it and we have to understand it. So, how does this communication take place? That is the question that I will explain. This happens through an optocoupler, and we will talk about it in the next video. In this video, we will talk about optocouplers. The component that you are seeing here, which I have in my hand, are quite universal optocouplers, so to speak. They can be used for almost anything. They are PC817S. How is it formed inside? It is very easy to understand. We are going to diagram and draw it right now. This component, as its name itself says, is an optical coupler. What does it mean? That it produces an optical coupling, that is, there is light inside it. This is our component. When we energize this diode, which this diode is an LED, I don't know if you knew, but LEDs, LED lights, in reality are diodes, only that in their internal excitation, instead of only blocking the passage of electrons, which they do, they also produce light there. When we excite this diode, we inject a voltage of approximately 1.5 to 3 volts. At this moment, this LED turns on, emits light, and from this side where we have a photosensitive circuit, it then activates and lets the electrons pass. I turn on this light, and from this side it lets the electrons pass. Why do we have this component so complex, so to speak, to carry out this notice from one side to the other? Think about the following. In this area of the board, we are already almost in contact with the control area with the microprocessor, delicate areas, and on this side of the board we are talking about that we have high voltages. These voltages, which are affected by the electric company if it has any problems, can damage a microprocessor. So, to warn from one side to the other how much is being consumed and how much the pulse width has to vary, an optocoupler is used precisely. This component allows that by means of a light it is informed from one side to the other, not being able to affect electrically what happens, neither from one side nor from the other. Precisely, this component has an internal barrier, that is, it has an internal dielectric, an insulation against electricity, a galvanic insulation of 5,000 volts. What does it mean? If for some reason 5,000 volts are injected from this side, nothing happens absolutely, and from this side the same, they communicate only through a light. This component is very interesting because we will find it several times in inverter technology. At least they will have 6 on all the boards. Excuse me, you will find 5, or rather 6 in some, depending on the type of fan you have. We will see it in practice and learn how to test this component. We will zoom in and illuminate. On the side where it has the point, we always have the LED that illuminates, And where the point is, we have the positive side of the LED, the positive side. Let's test with the multimeter to see if it is in good condition or not. We will place the multimeter in LED position and measure. Open line, perfect. And if we invert, we will have the voltage drop of the LED. The voltage drop of the LED is 1.05 volts. LED diodes have a voltage drop of a little more than 1 volt, generally, so this LED is perfect. On the other side, we would have open line, because now the LED is off. There is no continuity here. This is perfect. What would happen if we turn on that LED? We will test it with the necessary elements. We will use some special test leads. These test leads that we will be recommending can be purchased, and in the class that we talk about tools, I will explain a little more. There we have the part of the optocoupler that has to be bridged when the LED is turned on. We will connect this to the multimeter now. There we are. Now we are going to turn on that LED. How are we going to turn it on? We will do it with a small button cell. In this case, I have the CR2032 model. Remember that these batteries on the whiter side have their symbol or plus sign well marked. This is the positive. Notice that if we put in continuity, what will appear on the screen? There we have 20 ohms, and there it falls to 0. When the internal LED is turned on, continuity is produced on the other side. It is not a 0 to 0 continuity because in reality it is a photoreceiving circuit. It is not a direct bridge or a contact. That is why it always has some resistance, but it is very low, only 20 ohms. In this case, this optocoupler is working perfectly. If you want to see how it is made inside, I will show you one disassembled. This is how they are made inside. On one side it has the LED, and on the other side the photoreceiving circuit. This is how they communicate internally and can be turned on as we are seeing now. This is the dielectric material, the insulating material. If we energize it, we will see how the light turns on. But in this case it will be difficult because with the camera that we are making these recordings, it is a slightly more advanced camera and does not see infrared lights. But with any cell phone, perhaps Samsung or Xiaomi brand, you could see this light, just like you see the light of a remote control, just like that, they are infrared lights. With optocouplers, we will be talking about a circuit that is zero crossing detection, a very important circuit in electronic boards. To help you understand what zero crossing detection is for example, in air conditioning it serves to regulate the speed of the internal fan. When you have that normal AC fan with a blue capacitor on the board or a gray one, this zero crossing detection through an optocoupler serves to identify and make it change its speeds. But when we talk about forcers fans, we will be detailing its operation a little more. For now, what I will explain is zero crossing detection, which is a part of the board that I mentioned to you when we were tracking tracks. It works as follows. Again, we have to redraw our famous rectifier. Alternating current. Direct current. And here we have the capacitor. But remember that at this point we will have a fifth diode placed, as it was in the sample circuit. Do you remember? Here we have a fifth diode, as we had in this sample circuit. It is placed as follows. This will be negative and this will be positive. And here is where you will find it. Of course, there are 4 more diodes. At this point, taking as a comparison the negative the electron input, between these 2 points we will have the unfiltered rectification, as we could see in the class that we did the measurement with the oscilloscope. What does this point allow us to do? Let's observe. I will mark with a different color so we can notice it. We will go out from here, jump this, and we will go to a lead. We will jump from this point to here. We pass here and then we go back to the lead. And on this side, we will have a phototransistor. What is this? Precisely the optocoupler. Remember that on this side we are having this. What does it mean? That every time electrons are sent, they will pass through the lead and the lead will turn on. And 100 times per second or 120 depending on its frequency, that lead will turn off. That is, during all this time this lead remains on. By here the electrons pass. When this lead turns off, the electrons here stop passing. And what is on the other side? On the other side we will find the following. On the one hand we will go to the negative or G and D. And on the other hand we will go directly to the microprocessor, the integrated circuit. And here we go to 5 volts that are already generated by the circuit for everything we have already learned. These 5 volts will come to the microprocessor as long as they cannot go to the negative and a short circuit is produced. In reality, the short circuit does not occur because there is a resistance that may be 1 kilo ohms. We will talk about resistances later. Whenever this is on, the 5 volts will be diverted to the negative. But whenever this lead turns off, this is cut off and these 5 volts enter the microprocessor. It turns off. 5 enter. It turns on. The 5 volts are diverted. As a result of this, exactly at the same time, the microprocessor will receive a pulse of 5 volts, exactly at the same time, that is, here. The microprocessor now knows when the alternating current is crossing 0 of 220, 50 Hz or 110, 60 Hz, whatever, but they know what times cross 0 thanks to this detection. And why do we put an optocoupler? The idea is that what happens here does not damage the delicate circuit of the microprocessor, so that is why an optocoupler is also used, to be able to make a very powerful electrical insulation for any problem that may be in the line. This is how it works. One more detail that we are missing is that at this point, from the positive, we will have a large resistance. Because precisely if we are not injecting 300 volts to the lead, then we will have a large resistance that can be of 150 kilo ohms, for example. We will see all this on the board now to be able to identify this circuit. If this does not work, for example, it may be that the AC fan stops working. I will show you this same thing on the board. Let's observe and follow up here. From this point, where we have this sample, notice that from here we will go to here, with a high value resistance. In this case it is this. And then we go directly to an optocoupler. This coupler, looked at on this side, is the lead. We can see it down here. Generally on the motherboard where this point is indicated, it indicates the number 1 of the optocoupler, the positive of the lead. This other one that is to inform the switched mode power supply about how much the pulse width has to vary, the lead is placed on the delicate side. In this case, the lead is placed on the side where the zero crossing is generated. That is, when we have to inform the consumption from the microprocessor area, the consumption is informed from the delicate area from where the microprocessor is towards this side. And when we have to warn of the zero crossing from the side of the alternating voltage towards the microprocessor, the lead is placed precisely upside down. We have 2 optocouplers, but in the opposite position. And if we wanted to measure it here, inside the board, we can also do it. We can test the LEDs at these points to see if they are in good condition. One detail that we are going to explain now is about capacitors. When we have to replace them, there are 2 important data that are exactly the ones that are printed on the capacitor, and we have to take into account when buying a replacement. These values, we have to respect different parameters. For example, let's explain about these ones that we have here. The manufacturer usually places capacitors that support a voltage 25% higher than the one that will normally work. What does this mean? You already know that in this area we have 220 volts in alternating current, but in reality the peak voltage to which it reaches is 310 volts. 25% more, we will multiply it by 1.25, and we are talking about 387 volts. The next value of capacitors, next standard value, is the value that the manufacturer will be placing. In this case, it can be seen that they have obtained 450 volts, so they have put 450 volt capacitors. In terms of capacity, when we are in areas of source that comes after rectification, which will fulfill their filtering function, the capacity must be equal or greater than the one we are seeing on the original board, because the more capacity it has, the better, the more it will filter. But there is a point at which physically the capacitor will not fit. In this case we have 2 of 10 microfarads. If I wanted to put twice the capacity of these capacitors by physical space, they will not fit me, but they will work well anyway. So, when we are in the filtering stage, we will place capacitors with voltage equal or higher than the one it originally has, and with respect to the capacity it must be equal or higher. Now, when we are in other parts of the board, such as for example in more delicate areas, including the switched mode power supply, from the capacitor that feeds the switch, in all other cases we already have to respect the values of the capacitor in terms of capacity, because if they absorb too much capacity it will not have remaining electrons to be able to deliver to the appliance they have to feed. For example, in this case, in the case of this capacitor, which feeds the switch, we have to respect its capacity very well. If we put it of greater capacity, the source will not work. Here we have a 50 volt 4.7 microfarad capacitor. Except in the filtering area, in the rest of the areas we have to respect the capacitor values to make the replacements. We always have to take into account those parameters. So, understanding this, we are also knowing the following. I will show you an external board so that you can see how these capacitors are. Look at this. These are 420 volt capacitors, but they are 100 microfarads. This filtering of the external board, like this rectification, which is produced with the rectifier, then a filtering is done to feed even the compressor and the fans. The capacitors are of more capacity to maintain the filtering of the wave, but they are bigger. Clearly it can be seen. This would work on this board, but physically it will not fit. Now, if I put this one here of less capacity, it will not work for me because it will not keep the wave. it will drop to zero and it will not be able to feed the compressor properly. These data have to be taken into account when replacing the capacitors. These are the parameters that we will be following to make the correct replacements. We are going to talk now about a part of the circuit that you will find in an inverter board, and this part is why many say that it is essential that we have a ground wire in inverter air conditioners. What do we mean by ground? The third wire of the electrical installation that has a connection to a spike. And why do many say that it is essential that inverter air conditioners have a ground wire? This is one of those reasons. To begin with, I will tell you that an inverter air conditioner can operate without any problem even if it does not have a ground wire. You can record that in your mind and do not forget it. An inverter unit will operate without any problem even if it does not have a ground wire, just like any other appliance. The most important function of the ground wire is the protection of people. In another of the modules of this course, it is clearly explained how the ground wire works together with a circuit breaker to never allow a person to be electrocuted with an appliance. But inverter boards also have an additional feature. Inverter electronic boards have a connection to themselves from the ground wire, but this is no longer for the protection of people. Although the equipment will still operate the same even if there is no ground wire, but I will explain why this is and also other components that are surrounding it. Well, I will make a diagram and then follow up on the tracks of these external electronic boards. This ground wire can also be found in the interior boards mounted on the board. We had said that at the entrance of the electricity, we had on one side a fuse and a varistor. Here's where the ground wire comes into play. In inverter units, we are going to give ourselves a little more space so we can draw it well. In inverter units, what we will have now is a slightly more complex circuit, always alternating current, and then we go to all the components that you already know, double pi filter, then comes the rectifier, etc. But in inverter units, we no longer have this, but something a bit more sophisticated and of better quality that does not allow the voltage to enter into a short circuit and the fuse blows. But it tries to divert this power whenever there is high voltage, excess of high voltage. It tries to divert it to the ground wire so that the circuit breaker trips. So what you will find is, we will not have this varistor here joining the two, but a varistor here. And here another varistor. Here we are going to go to a fuse. And here is where we are going to go to the ground wire. Here the circuit continues and everything else, but what is the purpose of this? If we have normal voltage positive and negative, they continue their path and feed the equipment. But if we have excess voltage, it will be diverted through one of the two varistors. We will jump this fuse, we will cross it, and we will go through the ground wire and the circuit breaker will trip. The circuit breaker will do is to trip and de-energize the equipment, thanks to this circuit. This protects it against high voltage. The system is good, well done. This that you are seeing here is a... I will put it in a different color and write it here. It is a vacuum device that does not allow any high voltage, or better said, does not allow any discharge from any other appliance to enter the inverter board. If another appliance is short-circuited, or better said, is grounded, that to enter through the equipment to the board, and so that this does not happen here, there is a vacuum device. This device allows the passage of electrons to that side. Whenever from this side it detects a very high voltage, a kind of lightning or spark is produced inside and it is diverted. When there is very high voltage in one of the two, line and neutral, it diverts through the varistors and goes through the vacuum device to the ground wire, and the circuit breaker trips. Well, this vacuum device and this circuit we are seeing here, of course the fuse is always there to act, but in reality the idea is that the fuse does not act and that this works and the equipment is de-energized in that voltage surge. The system is good, well thought out. It is not definitive and absolute, but it is a good system. Now we will see it on the electronic board directly. Look that here we have an inverter board, and here we are seeing the varistors. Span class equals QL cursor, and we are seeing here the vacuum device / span. In this video, we will follow the same circuits that we just explained on an inverter electronic board. So, observe that here we have the fuse. I'll zoom in so we can see it. Here we have the fuse, the two varistors. Here we have the vacuum device that I just mentioned. Here is the output to the physical ground, and this is the protective circuit. We will see it from the other side and follow the tracks. Here we have the varistors, the ground channel, and the vacuum device at this point. At this point we have the vacuum device, and here we have the varistors. This is the reason why it is said that we must have ground yes or yes in an inverter equipment. So, is it true that it is necessary? Yes, it is necessary because it protects against high voltage. It is not mandatory, the equipment will work the same. Keep this in mind to explain to customers. Ground has always been for protection of people and, in the case of inverters, it also protects electronic boards. This would be the explanation. Let's see this on an LG board. On this LG board, the reality is that it does not have a vacuum device. The LG board is a bit more rustic. It does not have as good quality as other boards, but LG has a good reputation. It does not need to do things so well already by fame it can sell. We have the varistors, and here is where ground is connected on channel 1, and here we have the fuse. Remember this important detail to be able to explain to customers about grounding. Perfect. Having explained this topic well, let's move on to do follow-ups on the outer plates so that you can now identify or understand how electricity travels through electronic plates. That's what we're going to try to do, gradually understanding all the circuits. You are seeing an inverter electronic plate here. Now I'll zoom in a bit. Starting on this side, I'd better turn it over because the words are written backwards. At this point here we have the line and the neutral. Here we have communication or signal. We'll talk more about that later. The line will go through a fuse and continue its journey, line and neutral. Here we have the varistors, here the ground discharge. The ground discharge also has a small connection with some capacitors that also do stabilization or final filtering. You can also see some small capacitors of this format on this side. We reach this point, cross from one side to the other the toroidal coils of the filter. We have some final capacitors again. Here we cross a small contact relay. Here we have a filtering capacitor for low capacity, capacitors, and finally with the two in the middle we reach the rectifier input, the alternating current input of the rectifier, and at both ends we already come out with rectified voltage. If we ignore some things that we have here in the middle, which I will explain later, we will then reach the filtering capacitors. Rectification, and here we have filtering done with capacitors, 8 of 100, they are 800 microfarads that are filtering this area. This that I just skipped is what we are going to talk about next, which is the power factor correction circuit, or PFC. We will talk about that later. We will do the same on the LG plate. I'm going to take it out of here. Well, here we have neutral and line. We cross a fuse. Yes, this is the fuse. Here we go towards the capacitors and the ground derivation we have here in this area, then to a winding and another winding. Look how these LG low-pass filter coils are a little smaller. Here we have a filtering capacitor too. It doesn't have two but only one. It's not double pi format. We continue our journey crossing a small fuse more, and what we do here is skip a component that is connected in these two cables, which is part of the PFC circuit that we are going to talk about next. This component produces a union of the two cables simply, but if we continue along the route we find alternating voltage or alternating voltage input of the rectifier. Here we can see the rectifier. And if we look at the rectified output, here we have negative that follows this route and goes towards here. And here we have the positive that comes towards here and reaches this end, and what do we have here? At this point we have the capacitor. In this case, this LG has only one capacitor of 680 microfarads, and here is where voltage is filtered. So here you have source zone of outdoor unit, but their source does not end. Remember that now we must go to switched source. These plates have switched sources. It is true, this filtering, this voltage of 310, if you have 220, it will go to the motor. We will explain that later. We still have to go through more components, but this will also go to the switched source. And if you observe, here we have the positive and here we have the negative. Look at the negative. We reach this side of this component and skip to the other side. This component of 7, remember that it was the switch. There we have the switch, and then we come to the ferrite transformer, to the coil of the ferrite transformer, and the positive. These arrows are only jumpers, that's why there is the letter J. It goes straight to it, to the transformer. I'm going to show you these jumpers on the other side. There you have it. Very well, we cross the transformer, and on the other side of the transformer, if we follow tracks, notice that we are going to find a diode here. There, I show it to you. Notice that we are seeing all this from above. What do I mean? That without disassembling almost anything from the air conditioner, all this is exposed to us, and you will be able to make all these visualizations. Here we have evidently an output from the transformer. It crosses a diode that must be half-wave rectification. We follow tracks, continue, and here we have this checkpoint of 15 volts. Between this point 15 volts and this one that says GND, I must have 15 volts. So this transformer has an output of 15 on one side. If we go towards another side, let's go towards here. Evidently this is negative. It is negative because it says GND, it is wider. Notice that this is all united towards here. It is united to all this is negative, and I have to find positive of 5 volts. If we go towards this side, we cross a component that is half-wave rectification diode. We come towards here, and we are entering this component of 3. Evidently this must be a 7805 because on this side that I know is output, notice that we are going exactly towards this point, which is a checkpoint of 5 volts. Evidently about 12 or 15 will enter here as well and regulates for 5. I'm going to show it to you on the other side, and we're going to identify these two half-wave rectification diodes. So here we have everything we just mentioned. Half-wave rectifiers, here we have filtering capacitors, and here we have 7805. There it is clearly visible. Well, as soon as I disassemble a unit, I don't have access to this part of the plate, but if I have access to the other side, and little by little you will become familiar with all this and will be able to do your tests from here. In fact, we are going to do some measurements in the following classes, and the idea is that you can also do them. My idea is always the same, that you can diagnose an inverter circuit without disassembling all equipment or disassembling as little as possible. With this we are finishing with what is source zone. Shall we go with the other plate? This electronic plate, after capacitors I also have to go towards switcher. This electronic plate is more complex because it has tracks on both sides, but still I will have many test points on this side. Notice that here there are a lot of checkpoint of 0.6 volts, of 1.8 checkpoint of 15 volts. Here I have another checkpoint of 12. What I don't see here is switcher. Here it's not visible because it's mounted on other side like a device that mounts without crossing plate. Transformer does crossplate and we'll see it on other side. In this case, in this plate, maybe it's necessary to disassemble a little more to make these measurements. But here we have the capacitors, the switch, the components that surround the switched power supply, and some electrical resistance. Those are diodes that do not cross. They are mounted superficially SMD. Here we have the optocoupler. Here we have the transformer, and on the other side half-wave rectifier circuit that has the mounted diode and the last capacitors. Here we are reaching the end of the source of the outdoor unit. Any problem in the source area, the electronic plate directly does not work because this is what prepares the voltage to power the microprocessor that commands everything else, that warns us of error codes, etc. Everything we've been seeing, the rectifier, capacitors, and switched source are part of source that powers control zone. In the previous video, we mentioned that in the circuit of the source we have some additional components that are connected with these two cables. The additional component that is inside the circuit of the source, but we can say that it is not the same as the circuit of the source, but rather it is in the middle of the control zone. This is the PFC circuit. The PFC circuit is composed visually. You will be able to identify it quickly in inverter equipment because what you will see is a reactor. This component is not a transformer, What it does is let electrons pass through it and come out, nothing more. What is its function? What problems does it bring in inverter? Well, if this component is in bad condition, the problem is not that the source stops working, but that it will mark some kind of error, such as overcurrent error of the equipment itself. You will always find this component near the motor compressor. I will show you an image so you can see where it is. You will find it here, near the motor compressor. If you don't see it, it is very likely that it is on the electronic board. It can also be mounted on the electronic board. Here we have it near the motor compressor, here we have the fan, and here we have it mounted on the board. The question now is, where is it placed? What problems does it present? How is it measured? What is its purpose? That's what I want you to understand most, what this component is for. It's key to being able to identify problems and understand how things work. I'll talk about that now. Perhaps you have heard about power factor. For example, when in a factory we have many motors, these are the windings of the motors that I want to draw here. What is done is to place a capacitor bank to compensate for power factor. Why? Because coils and capacitors alter electron flow, and this has something to do with low-pass filter circuit or double-pie filter circuit that we had been analyzing in previous modules. It has a lot to do because coils and capacitors function exactly opposite. You will remember that this represented, if we compare it with water, like a cistern, and this could be compared to a centrifugal water pressure pump. Well, what problems can these components cause in electricity? Surely you will remember that sinusoidal wave or electricity provided by electric company is a sinusoidal wave. So if we place many capacitors, what happens is that voltage lags behind. What does that mean? With respect to normal passing voltage, voltage delivered by electric company, due to capacitor charging, I am actually out of time and am over here. Let's see if I can draw it. I'll be around here approximately. I'm out of time. Now if we place motors or coils, I make voltage advance. So thanks to these motors or coils, I'm out of time again, but in other direction advanced. Either voltage advances or load lags behind can also be called. It can be mentioned both ways. Same capacitor lags behind voltage or advances load. It can be said both ways. My way of explaining it is that capacitor lags behind voltage and coils advance it. What happens with this? What happens when we place motors and capacitors? If I only place motors, imagine that we only place motors. Let's erase red representing capacitors. At some point in time, let's assume a moment in time for example here. Imagine what happens when the line voltage is pushing electrons to one side, to one cable, because these are altering the time. At that moment, these will be pushing electrons to the opposite side. So there are certain moments in time, I repeat, there are certain moments in time, that is from here to here, where the coils push to one side and electricity to the other. Here we are fine because we are on the same side. But here again if it hurts us again. You see that it is towards one side and towards another, always from this line I mean, which is voltage 0. There are moments then in time when the voltage is pushing to one side and the coils to the other. What do I do to compensate for this? What is done is to place capacitors. So what I do is delay the voltage a bit that was advanced by the coils, and then what I do is equalize this line and this line, I take it to that side, and we tend to equalize it exactly. There it went too far. So what do? We will want to equalize it. I'll see if I can do it this way. It doesn't let me, it doesn't matter. What we do is move back and equalize again. Now this that we are seeing here, this problem of push and our coils pushing to the other side, is a problem of power factor. What does this mean? In reality, I don't pay for it on my electricity bill. This is a waste or an extra force that I make the company that provides electricity do. What I do then is that my power factor is be down because of all the motors I am placing. What does power factor mean? For example, if they deliver 1000 watts of power, which are what I am consuming, I am taking advantage of little, I am taking advantage of 0.5. The power factor is always between 0 and 1. I am taking advantage of 0.5. That means that I am only taking advantage of 500 watts of power provided by the electric company for 1000 they are sending me. This is not paid on the electricity bill, but it hurts the company that provides electricity. That's why when in a factory there are many coils and no capacitors have been placed, in this case a fine is made to those factories. Well, if I place capacitors I correct this power factor and what I do is raise it. Then maybe I raise it and from 500 watts they deliver me I will be able to take advantage of 0.7, the power factor. Factor is always a number within a multiplication, it says factor. The power factor will be 0.7, so I reach 700 better thanks to capacitors. But placing capacitors, unless it's a computerized capacitor bank, aren't safe because it really depends a lot on how many machines are turned on at that moment. If I place capacitors taking into account all motors turned on when some motors aren't turned on, I'll run the line to the other side. In the end again I'll alter power factor. So placing capacitors isn't safest, but always help. If I have many capacitors in one place, my power factor is also altered, but what I have to do to compensate is to place coils. And that's exactly what happens in inverter, exactly the opposite of what happens in a factory. In inverter technology, as I have to filter voltages for high consumption, I have many capacitors that delay the voltage. So what is used to fix the phase shift in power factor? Well, what I place are reactors. The manufacturer places reactors that correct the power factor. That's why the reactor, although many call it coil, transformer, is actually a reactor. It is part of the PFC circuit correction of power factor. The capacitors are capacitive reactive loads. And coils are inductive reactive loads. If I have inductive loads, I have to place capacitive ones. If I have capacitive ones, I have to place inductive ones to correct power factor, which is this number. I have to raise it. The ideal is that it be 1. If they deliver 1000 watts and the power factor is 1, if I correct it exactly, I am taking advantage of all the watts they deliver me. It's hard to get to 1, but you can. Well, all these components, such as coils and capacitors, used as PFC, are called passive PFC. In all these parts of the course there are many new names, but you have the videos to review as many times as you want. Do it looking at boards, observing, review it well, because this is important to be able to make good diagnoses in inverter. If you don't understand how each component of the circuit works, it will get very complicated for you, this new thing, but little by little you will understand. Why is it called passive PFC? Because it is precisely passive. If I place a coil to compensate for capacitor work, that coil is a fixed correction, not a correction that adjusts all the time. So with this passive PFC, we will try to correct this power factor, and I will be able to reach 0.7 at most. So to improve this even more, what an inverter circuit will do, at least the most sophisticated ones, and for example all in Europe, will have an active PFC. There will be an electronic circuit that takes care of making this correction, helping the reactor, so to speak. Actually the other way around. The reactor helps a little the active circuit so that it doesn't force so much. Now we will see what we mean by this. We will see a diagram and also see it on the same electronic board in the next video. In this video, we will see a small diagram, very simple, and analyze how a PFC circuit is formed, which is always inside the source. Here we have it. It is quite drawn due to the previous training, but we are going to clean our board and be able to guide ourselves with this diagram. This is a diagram of a basic circuit with passive and active PFC, typical in an inverter system. There are parts that you know very well, such as, you know, the rectifier bridge, and you also know the capacitors very well. These are the rectifier bridges, and this represents the large capacitors in an inverse circuit. What will you find here? Here you are seeing that we have this coil. This is exactly the reactor. Notice that it is placed at the output of the positive of the direct current, which is then filtered with the capacitor. The negative goes straight. In the positive channel you will also find a fifth diode. Its function is also to divide what happens here from what happens here, as it happened to detect zero crossing, but now for something different. You will have this division of the fifth diode so that what happens on this side, the voltage or wave that is on this side, be different from this side, and a computerized circuit that is this one that is here can control and finish adjusting the power factor. Capacitors delay voltage, coils advance it, so it starts to adjust. But since an inverter system works faster or slower depending on the need, we will be using an active and computerized PFC circuit to finish adjusting the power factor and reach a power factor of 98. So if they deliver 1000 watts to me, if I were using 1000 watts, I would take advantage of 980 thanks to active PFC. How does it do it? Notice that this active PFC, that this component is inside the microprocessor, has a sample of this and a sample of this. And in turn it has a sample of this and a sample of this. Obviously it has resistances because it is high voltage, so it has large resistances to be able to detect a lower value but still see the wave. It has a fifth diode to divide from one side and another so it can measure zones separately, and what it also has is a MOSFET, perhaps the main component of an active PFC. which is a transistor that can transport high amperage. It's like a water valve in electricity, just like a water valve in water lets electrons pass through. So what's it going to do? He's going to know if electrons are going that way or that way, and he also knows if they're going there or there because of the capacitor effect. He also knows what happens on the line. He knows if electrons go one way or another. If at any moment he detects that electrons are coming here, and from this side they are coming here, what he's going to do is drive through the MOSFET so they go the other way. So if at any moment electrons collide, he diverts them and allows them to go towards the corresponding side in the incoming voltage. Thanks to that, there's never that electron collision. There's never that, as I told you about being in different times and one pushing one way and another pushing another way. It doesn't happen, or almost doesn't happen. That's how an active PFC circuit works. It's very efficient. It's a great system, but it's a delicate system because this MOSFET transistor, notice that this MOSFET transistor is constantly short-circuiting. That makes this component heat up quite a bit. This diode is a diode that is transporting many electrons because after here comes the switched source and motor compressor. It supports a lot of amperage. Everything heats up a lot and tends to burn out. That's why the circuit is good, but it gets damaged quite often, so we have to learn to check them. Now we will see all this on the electronic board, making the corresponding measurements. We will see it in the next video. As I said, we will see how to control a reactor, how to measure it, and how to know if it is in good condition. With regard to reactors, you have seen in the circuit that the only thing they do or have to do is to let the electrons pass, only producing a small modification in the time in which they will travel. Therefore, a reactor has to let the electrons pass almost freely. It does not have to have resistance to the passage of the same. If it starts to have resistance, we will have problems in an inverter electronic circuit, and those are the cases in which, for example, we have overcurrent errors. So if you have overcurrent error or even low voltage, check the reactor. If you have a low voltage error, I refer to although the voltage is in good condition, we place the multimeter in resistance and the resistance has to be almost 0.6. Notice that the multimeter only has 0.3, then 0.5, 0.4, almost 0 in its resistance, so it has to be. And obviously towards its housing it has to be open, completely open. There must be no continuity. Any defect in this causes us errors in the systems, errors that the board does not know how to say. What do I mean? These are the type of errors that the board will not say reactor error. You have to understand it, because you understand the operation. And of course, any technician looks here and finds a resistance perhaps of 2 or 3 ohms and says, well, this is fine, it has continuity, but 2 ohms is too much, there has to be less. And there is the problem. If this becomes faulty, it can be due to several reasons. For example, it got wet and went into a short circuit. Or for example, another error. Here there are solders between copper and metal. This solder can be carbonized, so in this case you have to clean it well. When we talk about welding, you will learn how to do these cleanings and how to solder again and how to use this year of good quality to put these parts back together. This is in sight in this model, but in some models it is hidden and I will show it to you. In this model those connections are hidden. Here you have to disassemble that paper and solder again those unions between copper and iron. In case you have to replace it, The value that you have to see and take into account are the millihenry and the ampere. These are the values to take into account. The millihenry have to be as similar as possible, and the amperage has to be equal or higher. The larger the equipment, the thicker the copper filaments will be. Well, this in the case of the reactor, which is the simplest component to check, but we also have the fifth diode and we also have the transformer. So now, in the next video, we will see how to do these measurements. As I said before, we will see how measurements are made on the diode and the MOSFET transistor. First, let's see where they are placed. Remember that we will find the reactor on the positive side. Also, the fifth diode and the MOSFET transistor will be joining the positive and negative. It will be in parallel. We will do some follow-ups. Over here we have alternating current, direct current output. The positive will reach L2. Whenever there is L, there is a coil or an inductance. We go through to L1. These are these two cables. This is where the reactor is placed. Continuing our tour, notice that here we have the positive and here we have the negative. This indicates to us on the board that this is the negative pole. And here is where we have the report that will give or the activation, which is given through the microprocessor to be able to activate and produce that bypass short circuit. Moving on, we don't see the tracks because they are on the other side. We have here the positive and here we come out of the other side of the diode. This is the fifth diode, transistor and fifth diode. Here we can see them. It's a little dark. I'm going to put on the light. Here we have the diode and here we have the transistor. I'm going to zoom in a bit to see it better. Rectifier, transistor and fifth diode. This IPM component we haven't analyzed yet. Now, how are we going to make measurements on these components? We must remember that here we go towards the positive of the capacitors, around we have the negative, and in the middle are the positives. From the diode we go to the positive. Here we have the active PFC circuit. How are we going to measure these components? We will even be able to measure how it is detecting at this checkpoint the sinusoidal wave. For all these measurements, please pay attention to what I will be showing you. We will see it from here. This is how you measure a transistor. You place a multimeter in resistance and measure between positive and negative, and a transistor's resistance must be in megohms, as we can see here several megohms, 5 or more. It is measured between positive and negative of MOSFET transistor or where short circuit occurs. A resistance similar to what we found in switched source switch. We continue advancing. Make that measurement and I'll let you continue with video. To control a diode is simple because you already know how a diode works. It lets electrons pass one way but not another. This way you control PFC diode. For one side lets pass and for other no. Voltage drop is lower because it is a diode that handles more amperage. So internal components, so to speak, are larger and let electrons pass a little more, so voltage drop is higher than 1N4007. You remember first classes, so its operation is controlled. If a defective dissipator is removed, with these screws and see what code component has. They are super fast high amperage diodes, and other one is high amperage MOSFET transistor, so you have to get exactly same good thing they get. As you could see, this is how it's controlled. Look with oscilloscope, how it oscillates at that checkpoint, or how we can see that circuit working with motor off. Can see it oscillating approximately at 100 Hz, which is number of times it crosses zero. Advancing the video, we will see when the motor starts to work, that's when it activates and starts to indicate at what moments to create that short circuit. There we can see that the PFC circuit is working well. This is also handled by PWM. It is always handled by pulse width. So this is what you will detect if you do a checkpoint on that third terminal of the MOSFET. There you will see a frequency of 100, and when the motor turns on, which is when that PFC has to be activated, there is when you will see a square PWM wave, which creates that short circuit to adjust the power factor. This is how it works. It is interesting to understand how it works. Why? It is difficult to detect when this circuit fails. It is difficult to say, well, the problem is the PFC. One blames anything, the voltage, the motor, the IPM, which is what most people know, but this PFC circuit is there and also tends to fail. Here we can see, on a carrier board with the reactor mounted on the board, you are seeing the rectifier. The transistor is Q, this one. And the one with the letter D is the diode. Detect that there is always some low-value resistance that works as a fuse. These are low-value resistances that let electrons pass through. There is always some resistance like this placed in these areas as a fuse, so keep that in mind. Excellent, so far we have advanced quite a bit. One last detail, on certain electronic boards such as LG, there is no active PFC. As there is no active PFC, they place a reactor to correct power factor a bit and place it here on alternating current at input. Keep in mind that detail if you don't see active PFC. For example, on this LG board I'm going to show you now. If you don't see the active PFC, it's not there because there is only a rectifier and IPM. In this case, they place it on alternating current. There's where they place reactor. Here's where reactor is plugged in. It's placed before. Anyway, there won't be any active PFC that has to control anything. Keep in mind that detail. They place an approximate and let whatever happens happen. Different from other board we were measuring that places reactor, checks how it works, and with active finishes adjusting, but parameters are same. Always have to check they're in good condition, and if those welds have been damaged, redo them. In case reactor is mounted on board, it's very difficult for it to fail. It's very rare, like in case of carrier or mirage. Span class equals QL cursor. So far we've been looking at reactor, talked about whole PFC circuit, and will continue advancing with stages of electronic board / span. Excellent. Advancing with this training, we have reached a point where we need to see how the path of electrons continues inside an inverter system. Let's pay attention to this detail. At this point, we had a rectification that is not being transformed, as you already know very well, from alternating current to direct current. Do you remember? This was an important transition in any board, and it is called rectification. Because this direct current is going to be consumed a lot, there is a PFC circuit or power factor rectifier, and, of course, to create a filtered DC, we will also have a capacitor. So here we already have a clean DC voltage, ready to be used again. Where are we going now? Well, now we have to keep moving on to the next components. On the one hand, we are going to go to the switched mode power supply, which I have already explained in the previous lessons how it works, what it is for, and how it finishes preparing a lower and regulated voltage so that the microprocessor works. So what we find is the switched mode power supply on the one hand. I'm going to draw it for you. And on the other hand, we find another component. Let's try to make a diagram. With this color better. Let's do rectification. Transform AC to DC. Very good. Afterwards, we will go through a PFC circuit, power factor rectifier. Afterwards, we are going to go on one side towards the switched mode power supply. And on the other side, we are going to go towards the IPM, and that is what we want to start talking about from now on. What is the IPM? Well, the switched mode power supply is the one that will give voltage to all the low voltage components and even the integrated circuit. And the IPM is the one that will prepare the voltage or the one that will finish giving the voltage or electron configuration for the compressor. So, this would be a diagram in broad strokes. The current is rectified, it goes through a PFC, and from there we go to a switched mode power supply, which feeds an integrated circuit. This is the team's computer, the brain. Now, the integrated circuit works together with the IPM to tell it at what speed the compressor has to turn. But look at this detail, how important this is, because previously in a conventional team to feed the compressor we did not go through all this. Before in conventional teams, to feed a compressor, let's see if we get it, we had alternating current, that is the one that comes from home. Now an inverter, the alternating current is not mentioned because it is not useful to us for anything. As soon as it enters you have to rectify it, but previously the alternating current was used. In fact, the alternating current directly went to feed the compressor. And we had on the other hand, rectification. We had the switched mode power supply and we had the integrated circuit. Integrated circuit, I refer to the processor. I'm going to show you, I refer to the microprocessor, the brain that commands everything. Now look how we had an integrated circuit previously, the only thing that is the circuit and will be, in the case of the compressor, was to enable or disable the passage of alternating current to the compressor. Well, the same thing was towards the fans. And the same thing was if each part of the team everything was fed with alternating current, we only rectified for the integrated circuit. But now an inverter, no. Now, a gate, that is the one that commands the integrated circuit and turns on or off. Now an inverter, as we were talking about just now, it is rectified, the power factor is corrected for the entire team completely. In fact, something additional, a preview of something that we will see later, we will also be passing through another IPM to feed the fan, both inside and outside. IPM does not know what it means, do not worry about this, it is something that we will talk about next because we want to reach with all our journey towards the compressor and towards the fan, but before explaining how the IPM works, I will explain to you how the inverter motors work, because it is essential that you understand how the inverter motors work. Both the gas compressor and the fan work the same. And there, if you are going to easily understand the IPM, what its work is and how the integrated circuit gives it the notice to turn faster or slower. Well, in the next video I will talk about how inverter motors work.